In this video, we're going to talk about source transformation as part of the fundamentals of electrical circuits. So typically in engineering and electrical engineering specifically, we like to come up with models where we can use, so we don't have to worry about the complexity of the bigger signal. So that's kind of where we are headed to. But before we get there, we need to talk about source transformation. You see there's the circuit on this side, as you can see, and then there's the circuit on this side. We say that these two circuits are equivalent to each other. Typically, we refer to this form where there's a voltage source and there's a resistors in series. We refer to this typically as a Thevenin equivalent. And when we form the circuit like this, where you got a current and you got the resistor, notice that the resistor is exactly the same value as the resistor there. And we could usually call this the Norton equivalent. And in later videos, you will find how we can take any given circuit, and reduce it. As long as we're interested in 2 points in the circuit, we can reduce it to either one of these configurations. So what we are here to talk about is that we're gonna try to show that the Thevenin equivalent, this circuit, is exactly equivalent to this circuit. So this is kind of what we are trying to prove. Now, what does equivalent means? Equivalent basically means if I put a certain current in here and I put exactly the same current in here, I'm going to get exactly the same voltage here as I get here. So that's really the equivalency that comes into play. So if I can prove that the current, any current given to the Thevenin equivalent would produce the same voltage as the Norton equivalent, or vice versa, I can put a voltage in there and get the same current, then it's said that these two are equivalent to each other and we can interchange them if we choose to. Okay, so now so how we do that? Well, we have a couple of techniques we can use. We can say, okay, let's make our life really easy, and we're going to take this Thevenin equivalent that is given, and we're going to have nothing across here. So we're going to leave A and B open. So if we leave A and B open, what we're going to see? We're only going to see a voltage that is over here. And that's, by the way, the reason this is called V open circuit. Sometimes they also refer to this thing as V Thevenin, but the V open circuit is more descriptive. It means the circuit is open, I'm going to get V open circuit. Now, in order for me to get the same V open circuit here, in order for this, we said if I is equal to 0, when this is open, I is going to be 0. The idea is that if I is equal to 0, V open, I should be getting a V open circuit here. Now the question is, what has to be true for me to get a V open circuit? Well, we know the Ohm's law. If this current is coming up here, there's nothing going here, based on Kirchhoff's law, the current down here also have to be I short circuit. Therefore, for this to be true, V open circuit has to be I short circuit times R Thevenin. Okay, so basically another way of thinking about this is it says that R Thevenin ought to be equal to the V open circuit over I short circuit in order for this to be true. And that's the only thing. If this is true, then these two are equivalent to each other. Sometime you may see this is done just a little bit differently. You could also say, okay, so if I were to short A and B for the Norton equivalent, and then come over here and do the same thing for this one, okay, so if I'm shorting it, what is my V open? What's the VAB here? VAB is equal to 0, and so I expect that when I do this here, the current that flows through here, since this R Thevenin is not 0, all this current will find the easy way out, so this is going to be I short circuit. So I better be getting I short circuit here if they are equivalent. So now let's go ahead and go over here and take a look at this and say, okay, in order for these two to be equivalent, I short circuit has to be what flows through here. So therefore, we're going to do a K VL around this loop with I short circuit being the current. So we're going to get minus VOC is equal to plus R Thevenin I short circuit has to be equal to 0, which again, R Thevenin is going to be equal to V open circuit over I short circuit. Okay, great. So now we prove this condition is true only if we can guarantee that R Thevenin is equal to V open circuit over I short circuit. Okay. So the main reason we talk about this is really kind of as a way of introducing Thevenin and Norton equivalent and saying that those two configurations are exactly equal. But there's a side benefit. Sometime in some circuit, also although it's not very effective, but in some circuits we find that it is a little easier. We are able to use this idea to simplify a circuit. For example, somebody gives you a circuit that looks like this, let's say. Okay, and this is 10 ohms, let's say. This is 100 ohms. This is 5 volts. This is 10 volts. And they'll ask you, okay, analyze this circuit and tell me, I don't know, what's the V open circuit here? Well, I could do an analysis on it and try to send KCL, KVL, all of that stuff on it, but it might be easier if I just use the source transformation and say this is A, this is B for this one. So I can really rewrite this one as a current going up and a resistor. So I'm going from a Thevenin equivalent to a Norton equivalent. And so therefore, I here has to be 10 I short circuit is V open circuit divided by R Thevenin. So it's going to be 10 volts divided by 10. So it's 1 amp. And of course, this is just going to stay the same because that's R Thevenin for that. And what I can do, I can take this circuit here and do the same thing to it. And I'll end up with current going up here. And it's going to be 5 over 100 in this case. So it's going to be 0.05 amp going up. And then my resistor is going to be 100 ohm. And so then after that, this becomes a relatively simple configuration. This current and this current add to each other and becomes the current up here. And the 100 ohm and 10 ohm are in parallel. And if you recall, parallel is 1 over 1 over 10 plus 1 over 1 over 100. And hopefully that's right around 9 without having to go do the calculation on it. And so that becomes our circuit as we reduce it. And here the current is going to be 0.05 plus 1, so 105 amp. So now I know what my V open circuit is because this is open, no current is going to flow here, so all the current is going to go through here. Or if you want, you can do another transformation, this time back to Norton, to the Thevenin equivalent from Norton. So our Thevenin is 9 ohms, and this is going to be 1.05 times 1.05 times 9, which is going to be your V open circuit. And there you have it. You have it. So another analysis tool in your toolbox. So far, earlier we had talked about KCL, KVL, Ohm's law, or node voltage method, mesh current method, and here is another one for you to remember. But again, the real important thing and the reason we cover this has to do with the fact that these two circuits here and here are equivalent to each other, because whatever, if you apply a voltage here and the same apply voltage here, you're going to get the same current, and vice versa. If you apply this currents, whatever equal currents here and here, you're going to get the equal voltage and voltage that out of there. And the requirement for this thing to be true is that R Thevenin has to be V open circuit over I short circuit. That brings us to the end of this video talking about source transformation.